So, good afternoon, everyone. I welcome the course coordinators and the course participants across various institutions. So, today's lecture is on Indian Regional Navigation Satellite System, that is IRNSS, whose operational name is NAVIC, Navigation with Indian Constellation. Today's lecture will be taken jointly by myself and Shri Kamal Pandiji. So, the learning objective of the today's session will be to cover up the basic IRNSS and NAVIC elements. What is IRNSS? The difference between IRNSS and Gagan. What are the positional accuracies from IRNSS which we are able to achieve? Some of the applications and case studies. So, as we have already covered the global navigation satellite system, satellite based augmentation systems in the previous week, today we are getting ahead with the Indian Regional Navigation Satellite System, which is a system totally developed and owned by Government of India. The system has been developed by Indian Space Research Organization, and it provides the PNT services, that is position, navigation and timing services, to the users in the entire Indian mainland and up to 1500 kilometers beyond Indian boundaries. And the accuracy with which we are getting the observation, it is of the range of 20 meters. On a very conservative side, you will find that the accuracy is between 5 meters to 6 meters also, if you will operate. However, the conservative measure is up to 20 meters for 24-hour basis. IRNSS also provides two types of services. One is the standard positioning service for the civilian applications, and another is for the authorized agencies, which is the restricted service. So these services are available 24/7 for all the users across India and in its footprint region also. The major objectives are as follows. It provides reliable position, navigation and timing services over Indian and its neighboring regions. It is designed in a way that most of the constellation is seen by all the users in the footprint region, and the system is independent of existing GNSS systems. So as we have seen in the Gagan lectures, that Gagan, the primary feed is from the GPS. There is no such requirement in the IRNSS. IRNSS has its own satellite constellation, fully independent to function irrespective of any other requirements. So IRNSS has about 8 satellites in the orbit now, out of which one is having an atomic clock issue. So 7 are fully operational. These are in the geostationary orbits and the inclined geosynchronous orbits. So we have 3 slots in the geostationary orbit and 4 satellites we have launched in the inclined orbits, which are fully operational. Now the IRNSS satellites are providing terrestrial, aerial and marine navigation services and helping various agencies and individuals during the disasters and for the fleet management across the region. The first satellite under IRNSS program was launched at a cost of about 125 crores. The constellation got completed between 2013 to 2016. The latest satellite is the IRNSS 1I, which was launched on the 12th April 2018. These satellites have an approximate life of about 10 years. So as explained, the services are primarily of two types, that is the SPS and the RS, that is standard positioning service and the restricted service. So L5 and S band are being utilized for the IRNSS services which are allotted by the International Telecommunication Union. The recent development is that now we have the L1 permission also. So in the upcoming IRNSS missions, we are going to have L1, L5 and S band. All the 3 bands will be there, which will further enhance our interoperability with the other GNSS constellations. The IRNSS Signal in Space ICD, that is the Interface Control Document for SPS, was released first in August 2017 and later the latest versions has also been released. Besides this, the ICT for disaster alert was also released in February 2021. So these ICDs are freely available and they are downloadable from the ISRO websites. And as these ICDs detail the signal structure, these can be utilized by the various app developers who want to make their own applications and programs based on the IRNSS services. Then IRNSS provides us the navigation data, which includes the satellite ephemeris, satellite clock correction parameters, satellite and signal health status, user range accuracy, total group delay as the primary navigation parameters. Besides these, there are secondary navigation parameters also, like the satellite almanac, ionospheric grid delays and confidence, which provides us the position of all the constellation satellites in IRNSS. Then IRNSS time offsets with respect to the UTC and the GNSS, because we have our own set of timing with our atomic clocks. So the variation between the UTC, International Coordinated Time, Universal Coordinated Time, and the GNSS time, those offsets are also built in the secondary navigation parameters. Ionospheric delay correction coefficients are there. Different text messages as per requirement, and differential corrections along with the earth orientation parameters. So all these constitute the secondary navigation parameters. So these are required during the different type of processing while obtaining the PNT services, specifically the positioning. So the IRNSS is providing the services for the entire Indian landmass. Besides this, it has an extended service area which lies between the latitude 30 degrees south to 50 degree north and longitude 30 degree east to 130 degree east. So you can see that we have a large footprint, and our neighboring countries can also benefit with it, along with the ships and various commercial vehicles within the ocean region also, Indian Ocean region also. So all these can take advantage of the IRNSS services and get an accuracy better than 20 meters in positioning. This is the screenshot for the Signal in Space ICD, which was released in July 2019, version 1.1. Already few of the applications are available for the fishermen if they are having the system with them during their movement in the ocean. So they can have the high wave service ID as the 0111, cyclone warning ID, and the tsunami ID also. So these are already available for the safety of the fishermen, provided by the INCOIS. Similar to the GNSS, which we have covered earlier, IRNSS can also be understood as a built-up mechanism having three segments. One is the space segment, which constitutes the different satellites. So in this space segment, we have IRNSS 1A to 1I. So we have, as of now, we have launched 9 satellites. So one satellite could not be launched properly. Rest 8 were placed in their respective orbits very accurately. Out of these 8, 7 are fully operational and providing the IRNSS services. Thereafter, we have the ground segment, which takes care of the satellites after the launches, and then we have the user segment. So coming back to the space segment, all the details of the space segments can also be seen through the ISRO website as shown on the screen, with the list of the satellites on the right hand side. So IRNSS 1A was the first satellite under the IRNSS series of satellites. Then it has two types of payloads, the navigation payload and the ranging payload. So navigation payload of IRNSS 1A transmits the navigation service signals to the users. This payload operates in L5 and S band. A highly accurate rubidium atomic clock is part of the navigation payload of the satellite. The ranging payload of IRNSS consists of a C-band transponder which facilitates accurate determination of the range of the satellite. And besides this IRNSS series of satellites, they have the corner cube reflectors also for the accurate ranging of the satellites. This table further details the payload specifications. So for more interest to the users, we have the listing of the L band and S band frequencies. So L band is having a frequency of 1191 megahertz and S band is having a frequency of 2491 megahertz with a bandwidth also. Besides this, for other communication necessities, C band is also utilized. However, for the navigation purpose, L band and S band are being utilized. Here also, like similar to the CA code of GPS, Navistar GPS, in case of IRNSS also, the PRN code is having a time period of 1 millisecond and it is the gold code. So this picture explains the setup which we are utilizing for the IRNSS. So we have 3 slots, one at the 34° east for the IRNSS, and then 83° east and 132° east. Besides that, 4 satellites are launched in the inclined orbits also, with an inclination of about 19° in the orbit with respect to the equator. So this also explains the same thing. So here the entire constellation was built between 2013 to 2016. Now we have a plan to further launch 4 more satellites so that the total number becomes 11, and we have more redundancy in the IRNSS constellation, providing us better accuracy. The design considerations for the constellation is as follows. It was designed in such a way that it provides us a good value of dilution of precision. So it should be minimum basically, and then optimal DOP is available for the entire service area with the help of minimum number of satellites in the constellation. And another condition is as per the orbital slots provided to the Indian agencies, because when we are launching the satellite in the equatorial orbit, then we have to seek the slots, so that also we have to take into consideration while designing the IRNSS set of satellites. So this figure particularly again shows that this is the space segment which has the minimum 7 number of IRNSS satellites. Then we have the ground segment where we have different control stations which we will discuss further, and then the third segment is the user segment, which can be on the earth or it can be in the air or in the ocean also, and even in the space, because the satellites are also fitted with the positioning receivers nowadays. So it can have GPS receivers or it can have IRNSS receivers too. After the space segment, next is the ground segment. So basically the ground segment carry out the housekeeping and station keeping of the IRNSS satellites. It carry out precise orbit determination, which is commonly known as the POD, for all the IRNSS satellites using one-way, two-way and laser ranging. So we have to determine the accurate position of the satellites in their orbit, because that will be utilized to compute the pseudo ranges, and further we will zero down on the position of the receiver after the intersection of the different spheres which we frame around the satellites using the pseudo ranges. The ground segment also generates, maintain and disseminate IRNSS network time using an ensemble of highly stable clocks. It estimates the onboard satellite clock bias and drift rate along with the ionospheric delay using one-way range measurement datasets. So there are a lot of activities which are taken care by the ground segment, from the collection of the data, corrections, and the uplinking of the various new softwares or any updates which are required. Ground segment is a huge segment actually, and lot of activities are there. So we have IRNSS navigation control facility, and then we have IRNSS satellite control facility. Now the navigation control facility has further tasks and components actually, which are the IRNSS Navigation Center (INC), then IRNWT, IRCDR, ILRS for the laser ranging, then the IRIMS are there for the range and integrity monitoring, and then the data communication is taken care by the IRDCN. The telemetry tracking comes under the satellite control facility along with the uplinking stations, and the entire operations are taken care by the IRNSS satellite control centers at Hassan and Bhopal. So first we will look at the objectives of the INC. So the INC estimate and predicts the ephemeris, that is the position of the IRNSS satellites in the respective orbits. It further calculates corrections for the satellite vehicle clock and maintain IRNSS time. It determines the ionospheric corrections. It maintains the integrity and transmit the clock and ephemeris corrections to the telemetry and tracking control command stations for uplinking to the satellites. Then coming to the IRNSS network time, that is IRNWT. The network time is derived from an ensemble average of atomic clocks, which is a combination of cesium clocks and active hydrogen measures. IRNWT is the reference for all types of corrections which are being computed for each of the satellites and the spacecrafts. Then we are doing the CDMA ranging. So the IRCDR centers take care of that. So it facilitates accurate ranging of the IRNSS satellites and send the data to the navigation control center. Further, the corner cube retroreflectors are being utilized by the laser ranging service, that is ILRS, to get the accurate distance of the IRNSS satellites. Then the ranging and integrity monitoring stations, they receive the data from the geostationary and geosynchronous orbits. They transmit the data to the navigation control center and facilitate one-way ranging of the different IRNSS satellites in the geostationary as well as geosynchronous orbits. Coming to the data communication part, so the IRDCN takes care of the data communication with a built-in redundancy into the system so that there is no failure in the service. Then the telemetry tracking command and uplink stations, they receive the telemetry from the IRNSS constellations. They telecommand the IRNSS constellations and they are used for the uplinking of the navigation updates. The satellite control center, they are managing the entire IRNSS set of satellites and do the entire maintenance operations also through the two centers, that is at Hassan, Bangalore and Bhopal in Madhya Pradesh. This is the schematic chart of the IRNSS data communication part. So this is a setup at Indian Institute of Remote Sensing at Dehradun also. Now the navigation center for the IRNSS, it is located in the Deep Space Network complex of the Indian Space Research Organization at Belalu near Bangalore. The navigation center is functioning as the main ground station for the satellite system. It is responsible for the time reference, generation of navigation messages, and further monitoring and control of the ground facilities, including the ranging stations. So after the space segment and the ground segment, the third segment is the user segment, and the user segment requires the different type of receivers. So currently we have this single frequency receivers which can have L5 band signals only or S band signals only. So they will be single frequency signal receivers. Then we can have dual frequency receivers which can receive L5 and S band both in the receiver. Now this is available for the civilian community, whereas the different restricted services are available for the authorized users. So they can also have the dual frequency L5 and S band IRNSS user receivers, along with the option of availability of other signals from different GNSS also, like the IRNSS and satellite based navigation positioning through the Navistar GPS, GLONASS and Galileo. So these receivers are also available, and as I have discussed, now we have received the permission of L1 signal also for IRNSS. So from the upcoming IRNSS satellites which are due to be launched, we will have L1, L5 and S. All the three bands will be there, which will help us in further interoperability between the different GNSS systems. So thank you. Now hereafter some case studies and other components will be taken by Shri Kamal Panditji.
Yes, good afternoon to all of you. Now, henceforth, I will be taking you towards two very good applications of this NAVIC signals. The first of all, let us try to understand what is this interoperability. So, which we talk about interoperability, it has the motto of better together than the separate. So, we have different kinds of this satellite system, navigation satellite systems across the in the space domain here. So if you can see, some of them are working in the L5 frequency, some of them are in L2, and we also have in the S band and L1 band. So like GPS is in the L1 and L2, and similarly the GLONASS, or if we talk about this Galileo, this also working in the GLONASS. So all these are working together, but the issue occurs that we want the availability of the satellite data. So if they all work together for the calculations of the location information, then that comes under the category of this interoperability. Means it is allows navigation with one signal from 4 or more systems with no additional receiver cost or complexity. Means I can get the location information computed not only from one satellite system or the navigation system, but it can take the signals from other navigation systems also. So it improves two things. The first thing is the availability, and the second point is the accuracy. So these 2 points are targeted through this interoperability. So that is a very good concept that is coming up not only in the space, this navigation domain, the same interoperability in other technical aspects also. So here also in navigation, our NAVIC system is quite interoperable with other navigation systems. So if we talk about the NAVIC and this Gagan and the NAVIC, there is a basic difference between the Gagan and the NAVIC. You can say that the NAVIC or IRNSS, it is an independent system. Okay, it is an independent system which gives us the navigational information, whereas Gagan is a separate system which augments the GPS signals in our receiver. Means I have a receiver which is capable of taking the signals from the GPS satellites. Now there may be some ionospheric delays or some other atmospheric problems are there, due to which the accuracies are not good in my receiver. So in order to improve these accuracies which occur due to this ionospheric delays or the atmospheric conditions, so what we do, we are having a set of control stations across the country. In the entire country, more than 15 control stations are there in the country which are continuously monitoring the atmospheric conditions. Now these atmospheric conditions and ionospheric conditions are monitored by this system, and they are sent to 2 of the geostationary satellites. Okay, and from these correction signals are then received by your receiver. So your receiver is having the GPS signals, and it also have the correction parameters from the Gagan satellites. Okay, once these two combine, the accuracy of your system increases. So this is the basic objective of Gagan. So what it does, it only improves the accuracy of your GPS signal, whereas IRNSS, it is an independent system. Okay, so now if you can see it here, ISRO has set up around 15 reference stations in collaboration with Airport Authority of India. So these 15 reference stations, they are continuously monitoring the atmospheric conditions, and based upon those monitoring, it is calculating or computing those correction parameters which are sent to the Gagan satellites, and your receiver now receives those corrections, and you get a higher level of accuracy from those GPS signals. So if you see how it works, data from IRNRS is transmitted to the INMCC. Now this data is processed by INMCC and sent to, these are the monitoring station basically, to the uplink stations. Now this INLS transmit the corrected GPS information and time synchronization signals to the geostationary satellites, which then transmit the GPS signal with an accuracy of order of 3 meter horizontal and 4 meter vertical. These are the design accuracy standard which has been set during the design of this Gagan system. So if you see, these systems are spread across the entire country here. So it covers the so by having such a spread of these stations, we are able to monitor the atmospheric conditions across the entire Indian subcontinent over here, and accordingly we have better accuracies of GPS signals from in our receivers, in the receivers. So when we talk about the IRNSS, the applications of IRNSS, where do we use it basically? So there are numerous applications where IRNSS or the Navik signals can be used. That Gagan, that is being primarily used by the Airport Authority of India for their landing purposes. They are using not only the Gagan, they are using some other systems also, but that is also aids to their the flight management task. But when we talk about the Navik applications, so it can be from the terrestrial, aerial or the marine navigation. Different kinds of navigations can be conducted using this Navik. It also helps us in disaster management. We have one case study that I will be demonstrating, wherein we have used this Navik signal for the disaster management. I think sir has already told you about the about the fishermen. Whenever they are when they go into the sea, and whenever they are near the boundary level, at that time a message is given to them, an SOS message is given to them. Okay, this is the boundary. Now they have to return from that point. So that is also one application of the Navik. It can also be utilized for the natural resource management, vehicle tracking, very important application here. So your now henceforth, I think we have our Navik receivers in the mobile systems also. That has gone to a very miniaturization of those receivers have taken place, and we can perform that. This vehicle tracking and fleet management can also be performed using the Navik signal, and this also provides us the precise timing applications where the precise timing is required. In those application areas also, that Navik signals can be used. Mapping, surveying and geodetic data capture, this is again very important applications which are being utilized by the Navik systems. If you talk about the terrestrial navigation for the hikers and the travelers, visual and voice navigation for the divers, scientific research like crystal movement or the atmospheric studies and crystal deformation, these are very advanced or the scientific applications which are being conducted using the Navik signals. They also provide us for the business solutions, and there are numerous applications. You can also think of what new applications you can do from that navigation signals or the navigational parameters which you are getting from the Navik system. So if we talk about the for the developers basically, if they want to have we also have released the APIs for the Navik signals, and they are coming at the level 29. So these from the developer point of view, now these APIs can also be used in for the development of different kinds of navigation mobile apps. So there also you can make use of these things. So if you see it here, like Map My India, ISRO had a good collaboration with Map My India. Now they have developed one mobile app which is available in the Play Store, and that can be utilized for analyzing these signals from the Navik constellation. So now here let us talk about one application, whether we have done any accuracy assessment of the signals. Yes, we try to conduct a small case study for the Navik receiver. So what we have done, we kept the Navik receiver at one place for 1 hour. Okay, and we try to notice the signals received from that Navik constellation in that receiver. So if you see, most of the entire 1 hour, we have got a very high level of accuracy. Most of the time it is hitting the same point. Okay, and this is not only for the L5, we have conducted it for the S band also. So both for L5 and S band, we have got a very good level of accuracy. Maximum time it was hitting only at the at a single point only. So this was the setup which we have taken. Initially it was like one receiver was there, we had one battery also there, and this was the display unit wherein your data can be visualized can visualize, and if you want to log the data, then for the data logger we have used one laptop over here. So the continuous data was logged into this mobile into this laptop, and then further it was analyzed. So if we talk about that, you can see here this particular receiver, we can say this is an antenna and this is that receiver. In that receiver, if we talk, so it has a very high performance. It was provided by the Accord. There is one private company called Accord. They have provided this receiver to us, and if we talk about the chip level accuracies of it, it has an active antenna ports for the interface to GNSS antennas. It can provide not only the Navik receivers, it has the capability of getting the signals from other constellations also. Like it was having the constellation, the signals from GPS, GLONASS, and these all can be combined for the navigation solutions. So this particular system we have utilized in our system as well here, in our case study basically. So when we talk about the different kinds of receivers here, so earlier we used to have currently also we have this dongle based receivers. You can just take up this dongle, you can purchase it from any company, like Accord is one example I gave you. So they are providing this dongle. Cost is also around 5 to 10,000 rupees, and this can be inserted into your mobile, in your laptop, and your laptop becomes a GPS or the Navik receiver itself. Okay. Now again we also have the Bluetooth devices as well. This you can carry along with any computing device which can interact with this Bluetooth, and your signals will be there in your computing device from the Navik signals. When we talk about this mobile phone, about a smartphone, Navik receivers in the smartphones. So the smartphones which are running on the new Qualcomm chipset, the new chipset that support the Navik, they include Snapdragon 720G. This is a very popular chipset which is providing the signal. If I talk about the mobile phone, so Realme 7 Pro, this is one mobile device which is having Snapdragon 70G chipset in it, and it is able to capture the navigation parameters from our Navik satellites, Navik constellation as well. Okay, similarly this Redmi Note 5 Pro with a Qualcomm Snapdragon 720G chipset, it also able to capture this Navik constellation signals. So apart from that, if your mobile is able to the chipset is 662 or the 460 Snapdragon, then also it will be able to get those signals of the Navik constellation. Now when we talk about this 3GPP, very important breakthrough is there. Like this is the global standard body for the communications here. It has approved the India's regional navigation system developed by ISRO, and the implication will be that of the acceptance by it will bring this Navik technology to the commercial market for use in the 4G or the 5G or the Internet of Things based applications. So so we can say our Navik signals are also now approved by the international standards body. So when we are performing the accuracy assessment, we can see it here, the RMSE error, we were able to get the positional accuracy. If we talk about, that was around 3.5 meters, and or the height accuracy we were having around 3.1 meter. You can say through this Navik we are getting the accuracy of the level of 3 meter as well. This was performed in around 2016, but now we have improved further into that part. So this particular slide shows you the sky plot of those satellites. If you can see this, in the same sky plot we have the GPS signals are there. IRNSS signals and the SBAS system. If you see it here, this red color, these 4 reds you can see over here, 1, 2, 3, 4 and 5. At this particular point of time, these are the 5 Navik signals which are visible in this sky plot, and the green one, they are the GPS. There are many, 24 satellites are there on an average. So these satellites you can see the sky plot. So ours are Naviks. The position of the Naviks are different from those GPS, but these all can be combined together. The third one, the SBAS, the Gagan satellites, they are also lying over here. This white color satellite, if you can see it here, this is from the Gagan signal over here. So this, in the same sky plot, we can visualize the location of all these constellations. So there are many receivers which are providing such kind of facilities. So if we talk about the data analysis in the kinematic mode, so what we did, we started from Dehradun and traveled along with that Navik receiver to the Gaurikund area here. You can see it here in this vehicle. We have mounted the receiver on the top of it, and these are the data logger. Continuously we are logging the data as well from there. And another now the speciality of this particular track from Dehradun to Gaurikund is that this track is around 280 kilometers, but the elevation difference is of only 1000 kilometers. Okay. Whereas if we talk about Dehradun to Mussoorie track, another track, here the total horizontal distance, the track distance is around 40 kilometers, whereas the vertical, the elevation difference is also 1000. So from Dehradun to Mussoorie, elevation difference is around 1000 meters. Same is from Dehradun to Gaurikund. So we have a very good topographical tracks we have got it here. So if you see, to cover this only this 1000 elevation difference, we have gone through various sharp bends over there. So like a snake, if you can say hairpin bends kind of things are, we face many bends over here. Whereas in case of this, there were deep valleys and ridges were also there while traveling from Dehradun to Gaurikund. So both kind of things, deep shafts, turns and curves were monitored over here, whereas deep valleys and the ridges, they were monitored in this particular track. So we were able to find out that if you see it here, this is the particular statistics or the particular visualization of those signals. You see all the signals are in the same line here. Now this particular image is one ortho-corrected image. Ortho-corrected image means this the features you are seeing over here, they have very high level of accuracy, less than 1 meter. Now when we plotted our the logged data from IRNSS, GPS or the Gagan, they were perfectly sitting on top of this features in this image most of the time. Okay, so now if we another application we talk, that is the application is based upon the Gagan. Basically now during that 2013 disaster, we were having there was a task assigned to it to monitor or to assess the disaster that has happened. So huge disaster happened in the Kedarnath valley. Now in order to map it, so we have used the concept of crowdsourcing. And crowdsourcing means there may be some inbuilt crowdsourcing with the data collected by the crowd. The people who are staying over there, let them collect the data for us on various disaster aspects. It can be a landslide, it can be a broken bridge, or it can be some damage to the houses, or it can be damage to the roads, these kinds of disasters. So now in these areas we require a very high level of accuracy. So initially we had one GPS, one mobile app which was designed for collecting the data from GPS. So we have integrated the receivers, the Gagan receiver as well, the location information from the Gagan as well in this particular mobile app, in order to improve the accuracy of those disaster hit points. So these all were collected, and in WIN, if you can see, this is one small application. This mobile app was able to collect the data in point, line and polygon form, and this project was known as Map the Neighborhood in Uttarakhand, or Manu, by the name Manu, this particular mobile app. So if when we plotted all those data set, you can see it here, around 16,000 data points we were able to get in 2 months of exercise. So 16,000 data points. Further, it was carried out, and we got more data points from that. And this all data points have the accuracy taken from the Gagan receivers as well. And these data sets were analyzed, and that report was submitted to the Planning Commission for another reconstruction work to be carried out in that particular area. So this is one application of where I was talking to you about the disaster hit area in disaster management, how these signals can be utilized. Okay, so with this, if we talk about the learning outcomes, we see that understanding the Navig system, constellation design and the services, ground segment we have talked about. We have also talked about the accuracy. I think sir will also continue into this part.
So as we have seen the objectives for today's lecture, so in this we have covered the various aspects of the IRNSS along with the applications and some of the case studies covered by Kamalji. And now you can have the query session. So you can send the questions to us, and after a break of 2 minutes we will continue with the question session. And you can send questions for all the lectures which has been taken place under this course from the first lecture on GNSS till today. So both of us will be available to you for any of your queries in this course till now.